In this video, I introduce proximal policy optimization algorithms. The goal of policy grading methods is to find the optimal policy pi theta that maximizes the expected episodic real-world yield, as shown here. The stochastic policy explained in this figure. The real-world return explained in this figure. Where gamma is a discount factor, RT is real-world at step t. S0 is the starting state and t is the time horizon. Policy gradient is defined as a derivative of G with respect to theta, as shown here, which is a function of policy gradient. The policy parameter theta is updated by using this formulation where alpha is the learning rate. The goal of any policy gradient method is to iteratively maximize G by gradient ascent. Transfer region policy optimization maximizes the surrogate objective L subject to a constraint to find the optimal policy pi theta instead of the original objective G, as shown here, policy pi, old policy pi, and the advantage function A are explained in these two figures. Where theta old is a policy parameters before the update. This problem can be approximately solved using the conjugate approximation to the constraint. The constraint optimization problem can be converted to an constraint optimization problem, namely a penalized objective, as shown here. However, the fixed penalty coefficient beta is difficult to select. Proximal policy optimization alternates between sampling data through interaction with the environment and optimizing a surrogate objective using stochastic gradient ascent. Let's LT denote the probability rate defined by using the policy pi theta and old policy pi theta old. So RT theta old is equal to 1. TRPO maximizes a surrogate objective of the conservative policy iteration, as shown here, which may lead to a large policy update. Hence, PPO modifies the objective to penalize changes to the policy that move RT from 1. PPO objective becomes here, where epsilon is a hyperparameter. The first term inside the mean function is a CPI surrogate function, and the second term modifies the surrogate objective by clipping the probability ratio, which removes the incentive for moving RT outside of the interval from 1 minus epsilon to 1 plus epsilon. The probability ratio RT is clipped at 1 minus epsilon or 1 plus epsilon, depending on whether the advantage function AT and caret is positive or negative, as shown here. This is for positive A and this is for negative A. The final surrogate objective consists of 3 terms, as shown here, where C1, C2 are coefficients. S is entropy bonus for sufficient policy exploration, and LT, VF is a squared error loss for value evaluation. The advantage function is used to select the optimal policy as shown here, where T is the length of trajectory segments. In each iteration, N actors collect the T time steps of data. PPO contrasts the surrogate loss on the N by T time steps of data, and then optimizes the surrogate objective with mini batch as GD for key epochs. Here is a PPO actor critic. The first part is sampling data through interaction with the environment, and the second part is optimizing surrogate objective. For more details, please check with these references. Thank you. Bye.